Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the previous videos we discussed how to prove particular statements using direct proofs, and recall that a direct proof was one that if we were given a particular statement in maths, that we proved it without modifying that original statement in any way. And as you might expect, we're now going to talk about indirect proofs, which are proofs that we construct by starting with our original statement, modifying it into an equivalent statement using some of the equivalences that we proved in the propositional logic section, and then by proving the equivalent statement, we indirectly show that we've proven the original statement. So that's what we mean when we talk about an indirect proof. It's one in which we prove an equivalent form of the statement and therefore in turn prove that the original statement is true. And starting or going back to the propositional logic section, we discussed some equivalences at the beginning, which were otherwise known as these equivalences called contradiction equivalences. And in fact, using those equivalences, we can construct a certain type of proof known as a proof by contradiction. So recall one of the first equivalences that we showed was that P, a single propositional variable, was equivalent to not P implies contradiction. So what does this mean when constructing a proof? How can we use this equivalence to construct a proof? Well, that is to say that suppose I'm given a specific proposition, and let's assume that that proposition is not true. So I assume that this statement that I'm wanting to prove is true. Let's assume that it instead is not true. And if I can show as a direct result of that assumption that that arrives at an internal contradiction within our mathematical structure, we must therefore conclude that in fact P was true, that in fact not P was false. So by assuming that not P was true, that arrived at a contradiction, and therefore we conclude that the original statement, namely P, must in fact be true. So let's see this in action with a specific example. And this perhaps is the most famous example of proving something by contradiction, which is to show that the square root of 2 is an irrational number. So how do we start? Well, let's assume that the square root of 2 is not an irrational number. So we're going to go towards a contradiction and assume that the square root of 2 is not irrational. In other words, that's another way of just saying that the square root of 2 is rational. And let's remind ourselves of what we mean by a set of rational numbers. The set of rational numbers is the set of numbers a over b, where a is an integer and b is a natural number. So if the square root of 2 is rational, we must conclude that it can be written as a over b, where a is an integer and b is a natural number. And let's assume here, without the loss of generality, that this a over b is an irreducible fraction. In other words, that is to say that there are no common divisors of a and b other than minus 1 and 1. So it's in its most reduced form. We can't divide it down any further. And why can we assume that without loss of generality? Well, by assuming that, that does not kind of restrict the proof in any way. It's very reasonable to assume that our fraction is in its most reduced form. It doesn't affect the proof in any way. So let's continue now and think about what the result would be if I square both sides. If I square both sides and rearrange that equation, we must conclude that a squared is 2b squared. In other words, we're saying a squared is even. Well, if a squared is even, we must conclude that a is either divisible by 2 or minus 2. And what we write here is this notation to say 2 divides a or minus 2 divides a, with this vertical line meaning divides. That is to say that a is either divisible by 2 or minus 2. So, kind of substituting above and squaring that into that expression, we conclude then that 4 divides 2b squared. And in turn, we must conclude then that b squared is even. In other words, 2 divides b squared. So if b squared is even, we must therefore conclude that b is even. In other words, 2 divides b, right? And why don't we have minus 2 here? Well, that's because b here is running over the natural numbers, and the natural numbers are strictly positive, as opposed to a that was running over the integers, which is why we had to include minus 2. But what have we got now? We've concluded that 2 divides b and 2 divides a or minus 2 divides a, and therefore a over b is reducible because they're both divisible by 2, which is in direct contradiction with our original assumption that we said that this fraction was irreducible. So we've arrived at an internal contradiction, and hence the original proposition must have been true. So that's the finishing kind of statement of our proof. We made this assumption that the square root of 2 was not irrational, and therefore concluded directly as a result of that, this internal contradiction, and therefore we showed that that can't be true, and because this is a proposition, and a proposition must be either true or false, it must have been that, in fact, the square root of 2 was irrational and not irrational. So that's one way in which to construct a proof by contradiction for kind of a singular propositional variable. Now, we also discussed in the logic section about constructing kind of contradictions or equivalences between contradictions of propositions of the form P implies Q, and we showed that that was in fact equivalent to P and not Q implies contradiction. So in other words, if we have a statement of the form P implies Q, we can prove the truth of that by assuming P is true and not Q is true, and showing as a direct result of that assumption that we arrive at an internal contradiction within our mathematical structure. If we can show that, then we will have indirectly shown that P implies Q is true. So let's see an example of that here. So we've got a fairly simple one here, which is basically going to say that we've got the proposition for all n in the naturals, if 2 divides n squared, then it must follow that 2 divides n. In other words, if n squared is even, then n is even. So how are we going to prove that? Well, let's do exactly what we just said a minute ago, right? We're going to assume P is true, that's the left-hand side is true, and the right-hand side is not true. So we've got here, suppose towards a contradiction that 2 divides n squared, and 2 does not divide n, so for every n in n. And we use this symbol here, kind of a vertical line with the line going through it to say 2 does not divide n. Well, since n is a natural number, and 2 does not divide n, we must conclude that n is odd. In other words, we can write n as 2k minus 1 for some k in the naturals. That's just another way of writing it as an odd number. Squaring that now, what do we get? We conclude that n squared must be 2 times 2k squared minus 2k plus 1, right? That's just some simple algebra. You can check that yourself. So what does that mean? Well, that means that n squared is in fact odd, right? So we've concluded there that it follows that 2 does not divide n squared. But in our original assumption, we said that 2 divides n squared. So we've got a contradiction, and because we've got our contradiction, we must conclude that the original proposition is true. In other words, that for all n, 2 divides n squared implies 2 divides n. That is, if n squared is even, n is even. And that's the finishing kind of point of our proof. We've shown by contradiction that by making the assumption that P and not Q was true, that arrived at an internal contradiction, and hence, therefore, it must have been that P implies Q was necessarily true. And that followed from our equivalence that we showed within the propositional logic section. So that's where we're going to conclude the contradiction video at this point. And I heavily recommend that you read the notes again about this. And in the next video, what we're going to do is we're going to address that other form of equivalence that we talked about, which was this contrapositive equivalence, which was to say that P implies Q was equivalent to its contrapositive, and use that to show indirect proofs. And then we'll finish off on one final point, which is not really about direct or indirect proofs, but is another way of separating proofs known as constructive and non-constructive proofs. So as always, I remind you, to read the notes after this video, and also to attempt any problems in the module handbook that relate to contradiction proofs that we've talked about in this one. So thanks very much for listening, and I'll see you in the next video.